Okay, hi everyone. I'm Perry Carter, your host for today's info session with BDPA, powered by BDPA Today with Popular Technology TV. As many of you know now, Exascale Day is tomorrow, October 18th. And it is the day that we actually celebrate people and organizations actively using supercomputing and computational science to change the world for the better. In this webinar today, we will highlight artificial intelligence, or AI, along with HPE, our HPC community, and achievements across industry featuring BDPA and JEF collaborations and related success stories. We will close with a question and answer session facilitated by Bryan Bemley and me. Following this, up next, over the next couple of weeks and into November, we have autonomous operations, AI and compute at the edge, and then we have edge to core analytics. And these will be our two closing info sessions featuring HPE on November 7th and November 14th, respectively. Now, this morning's industry presenter is Steve Heibein. Steve is the artificial intelligence lead for Hewlett Packard Enterprise, or HP. And before HP, he served as CIO, CTO, or Vice President of Engineering for 20 years at several tech and media companies. And in these roles, he oversaw AI machine learning, data analytics projects, the areas of life science, fraud prevention, natural language processing, identity theft, cybersecurity, and energy forecasting. Steve advises organizations such as BDPA and JEF on the use and deployment of AI solutions and regularly presents about high-performance computing and artificial intelligence. Steve, good morning and welcome.
Good morning.
Yes, sir.
Hey, well, I want to thank BDPA and Perry and also Jeff. Thank you, Bryan Bemley, for inviting me. I appreciate the opportunity. Today, what I want to do is sort of cover a little broad subject, but Exascale Day, obviously, and I want to talk about some use cases for high-performance computing and artificial intelligence. And before I start, I'm actually going to show a little video that I think is sort of helpful to get you in the mood for Exascale Day. And so, but understanding it, Exascale Day, it's basically, if you think about it, Exa, the beginning there, it's basically 1 and 18 zeros. When you think of it like that, it's a billion. And, without much ado, let me show you the video here. I think you'll enjoy this.
Humankind has an insatiable curiosity to understand how things work, how we work, how our world around us works.
Traditionally, supercomputers have been used to generate insight into scientific problems that we did not understand.
We're at the point where high-performance computing technology could really make a breakthrough.
It's really the space race of this century.
Scientific discovery went through several phases. At some point, people decided that computer models, also known as simulations, are a very, very important mechanism to actually answer deep scientific questions.
Supercomputers have hit certain thresholds over time.
Gigascale, terascale, petascale, soon we'll have exascale.
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 Exascale computing is the next frontier of high-performance computing.
What is Exa? Exa means 10 to the 18th, or a billion operations per second.
A billion calculations, flops.
Flops are floating point operation per second.
That's 1 with 18 zeros after it.
Around 2008 is when we broke the petaflop barrier. A petaflop is 10 to the 15 floating point operation per second. So now we're talking about getting to an exaflop. If you add all the top 500 supercomputers that are available in the world today, you get to an exascale.
So this is kind of crazy, right? When you think about it.
Once you have the ability to simulate an exascale level,
right now we're talking about 2021 as sort of the target.
Then you can find more answers to questions because you really haven't had the ability to model at that level.
Of course, other countries are working on the same research because whoever gets there first has the keys to innovation and discovery.
We can do an exaflop today, but it'd be very impractical. And so as we move forward, we'll need to do research leading to exascale technologies.
To talk about why we can't do more of the same, let's go back to the path we were on.
Over time, computers have become more and more powerful because we could pack the circuitry closer and closer together.
That's been working great, but at some point you reach a physical limit. You can't get the transistors any smaller. The other problem is that
moving data is costly from a power standpoint.
What does that mean? To do a calculation, you need the data.
The cost of moving data within the system is more expensive and more difficult than just doing the computation itself.
With today's technology, the Exascale supercomputer
would consume 650 megawatts of power.
650 megawatts.
That's the size of a small power plant.
This is not something that we can build using yesterday's architecture. We really have to rethink it from the ground up.
Our vision is to move the data much more efficiently and use much less energy.
We refer to it as memory-driven computing.
Memory-driven computing.
And that is one of the major innovations that we're working on at Hewlett Packard Enterprise.
So why Exascale? Why are we building Exascale supercomputers?
Some people wonder, what does it do for me?
A patient that might have cancer, for example, how can we find the right therapy for that particular patient in the fastest way possible?
In the past, the treatment for cancer was a shotgun approach. Basically bombard everything and see if by killing everything, you also hit the cancer cells.
Today, anybody that's got access to social media kind of understands the people you may know thing, right? Well, imagine doing the same thing for cancer therapy.
Patients would walk into the doctor, get tissue samples, get the DNA sequence.
And all of that gets pushed into a system that basically would be able to match your genome profile to hundreds of thousands of other people's profiles. And the doctor would be able to tell you the best outcome is really to go with this specific treatment.
And it could be the dosage of drugs, when the drug should be delivered.
The Exascale brings you the ability to ingest a lot more data to build that system that can be in all hospitals around the world to increase basically people's chances of survival of cancer.
Another great application for exascale computing is in the area of weather forecasting, weather prediction.
Today's weather models use a grid. With the computing power we have, we can reach precisions of maybe about 20 kilometers.
There's only so much we can do. There's only such a level of accuracy that we can have.
Scientists believe that they can build models that can get you to a few kilometers precision within the next 4 or 5 years.
The higher resolution you get, the more accurate your weather prediction is.
Then we can better respond and help those that are impacted.
A far more precise weather model, which could be enabled by exascale machines, can have a significant impact on catastrophic events and the response we can put in place to avoid them.
I think the use case for exascale in space research is one of the most exciting ones that we have.
The latest instrument that's being built, it's called the Square Kilometer Array.
The so-called Square Kilometer Array, which is a kilometer by a kilometer tiled with radio telescopes.
With the goal of mapping the visible universe.
So how much data is the Square Kilometer Array generating? Well, it's about an exabyte a day.
An exascale class machine is pretty much mandatory to be able to address that kind of data.
We then take this to the next step with models and simulations of worlds that we cannot see visibly, coupling that in with what we can see.
You can start to get a better sense of how the universe works, and even leading to things like
how the universe is born.
Each increase in order of magnitude is a big deal. And I like to think of it this way. If I can walk, I can explore my neighborhood. If I ride my bicycle, I can explore my city. When I drive a car, I can explore the country. And if I fly, I can explore the world. We're going to go explore the world.
Well, what's exciting about this is not that far out. I'll talk about a system that Hewlett Packard Enterprise is building through our Cray subsidiary. And in fact, over the past 4 years, we bought 2 supercomputing companies, Silicon Graphics, which was the #2 supercomputing company, and then we bought Cray, the #1 supercomputing company. HPE up until then was the #3 supercomputing company. But when you look at it, how big is Exascale? It's incredible. But what it takes is something like this. The Frontier supercomputer will be the first Exascale supercomputer. It'll be 1.5 exaflops, okay, in terms of what it can calculate, and that's floating point operations per second. It's generally how people try and calculate this, but think of it like a whole bunch of rack size or refrigerator size units all tied together. And to give you kind of a feel for the massive scale of this, okay, it's basically going to be, you know, it's very large in terms of it's about the size of 2 basketball courts when you cover it with these computers. So what you saw there would be the equivalent of the front row of Frontier, right? And you see the picture up there. It basically goes back and to the right for much longer. This is just an artist's rendition because it hasn't been built yet. But if you think about it, 2 full basketball courts covered with servers like this. Well, to tie that together, you need a lot of bandwidth. And so what ends up happening is there's going to be about 90 miles of cables within those 2 basketball courts just to hold these together so they can compute. And that the fiber that's going to be used, it's basically going to give you the bandwidth that's going to be basically 2.8 million times the fastest bandwidth you can get to your house today. So when you start looking at this thing, 2.5, almost 3 million times faster than what you have today. And put that in perspective, you see that 100,000 HD movies in 1 second could be transferred over that. So pretty amazing stuff. And then from a speed, if you sort of looked at it, you took every person in the world, all 7.7 billion people on Earth, and each one, if they were had the ability to calculate, make 1 calculation per second, it would basically take over 6 years to do what this computer is going to be able to do in 1 second. So, which is amazing. And some of the other things just for scale, if you think about it, it actually flows to keep this cool, because remember, all these things are generating heat. Every time you put electricity in, like a light bulb, heat comes out. Well, the same thing happens with computers. So what you're finding is it's basically enough to fill an Olympic-sized pool every 2 hours. That's how much water circulates through this to keep it cool. And if you took, you heard them say in the movie that if you took, this computer will be faster than the top 100 fastest supercomputers that exist today. That's how much faster this is, and that's why it's so exciting. Some of the things that are key is what can we do with this thing? And you heard talk about these weather, obviously. As you have more computation capability, you can do smaller grids to get more precise weather. Understanding these things in terms of climate, what you can do is you can do predictions to say, if we make these changes in the amount of CO2 that's let into the air, et cetera, what will this happen? And you can predict going further. The development of clean energy, a lot of the work that's being done on the development of wind and energy and fusion energy, et cetera, that's all being done on supercomputers for the original work to be able to develop that, and then we put it into practice. Life sciences, I'll talk more about some of the things we do with predictive medicine, et cetera. Manufacturing, creating safer products. You saw the crash testing going on there. And with the government, a lot of things we're doing right now, smart cities and smart utilities to be able to move the energy where it needs to at the time it needs to be made, and to actually save quite a bit of energy that way. So I'm going to do a quick fundamentals or tutorial about AI. And if you sort of look at it, when you think of in the broadest sense, AI is getting the computer to mimic human behavior, okay? That's pretty broad in that sense. But if you look at it, really, it's getting a machine, you can train that up to do things. So the early AI examples are really rule-based. What they would do is something like an expert system. And to make the computer act like a human, We used to interview a doctor, for instance, and say, okay, what's your triage? What would you do? So someone comes in, you say, okay, I need to check their pulse, their temperature, their blood pressure, and these things like this. Then you start asking, that's basic information. Then you start asking, what are your symptoms? Got a sore throat. Well, if you got a sore throat, do this. If you've got a, I've got chills, I've got whatever. So what you do is you go through that, and how the expert system acts like the doctor by asking the same questions and following that same decision tree that they would do. And that's very simple AI. And that was easy to do. You could do that on a PC back in the 90s without any problem at all. Not very sophisticated in terms of the math. It was like if, then, else. Then you got machine learning, where what they started using and applying more statistical methods. They do feature extraction to say, okay, for instance, looking at that, how do you describe a car? I want to identify a car. Well, a car has 4 tires, it has a steering wheel, has glass up top, has 2 or 4 doors usually, and that type of thing. Well, that would be more descriptive and do feature extraction. Well, to get even the next level, if you start looking at like deep learning and machine learning using neural networks, what they're now doing is using sophisticated math to sort of say, I'm going to give you a lot of data. I want you to find the information within that data. So if I give you all these pictures of cats and dogs and flowers and whatever it is, I want you to be able to, after I'm done, identify that this is a dog, this is a cat, or this is this breed of a dog, or this is a specific type of a plant. And so that's where neural networks say, I'll learn from all these other pictures. So from everything where I interviewed the person to in the end, I'm just interviewing the data. And that's how that would work as you go through there from artificial intelligence, machine learning, and deep learning. A lot of times you'll hear people talk about this just as AI to cover all of this. So fundamentally, what can AI do? And I think that's the thing is people go, oh, AI, it's runs robots and Terminator 2 and that kind of thing. Well, truth be told, it's just math. And when it gets down to it, what can, it can do these types of things. I can recognize stuff. What's this object? Or detect. Did something change? Classify. Where does this fit amongst everything else? Search for something. Where is this phrase or where is this information like Google does? Identify who is this in the picture, group things together, what things are alike, what's the best, what's the worst. You can see the recommendation, you like this, buy that, filter out unwanted content. In fact, we do this a lot when we're doing signal analysis, or even your cell phone. We use that to sort of say, I want to signal out this noise and to get a better signal. I can predict, I can forecast. Based on the past, this is what will happen in the future. And of course, you can optimize. Given these many different ways to do it, like I'm playing chess, I can do this move, this move, this move, or this move. I'm going to optimize for what would be the best, considering what I see on the other side of the board. But I mean, that's basically what you got when it comes down to it, the types of things. And we just apply these in different ways. An example would be in cyber. In cyber, I might all of a sudden try and detect something going on, or I might classify how this person usually acts when they're online. And when something happens, I do an anomaly detection to say, oh, what's changed? And so you can see how these can be applied. In fact, one of the things we did for cybersecurity, we use over 100 different machine learning algorithms to be able to classify everybody's use patterns and identify when they get out of whack. So if somebody starts doing something, this Snowden character starts using a thumb drive, and they've never done that before, and they start logging into some other places where they haven't been, even though they have permissions to do that, it just sort of raises a flag. And those are the types of things you can do with AI. Now, I just said it's just math, right? But when you look at it, there's things we can do like predictive analysis, and you start looking at taking the past and predicting. So I can say, okay, I want to, based on these inputs, predict the future. Regression, if you look at just the standard thing you used to do when you plot like a graph, you run a line through that, and that regression sort of says, okay, based on this, if I'm given a new point, where it would lie on there, I can predict where it would lie on that line. So, and then classifications are more a matter of saying, I've got a variety of things here, and I could classify, I've got fruit. I could classify fruit by the shape. I could classify it by the weight, by the color, by the sugar content. So what you do is you let AI sort of classify these things in a different way. I use that classification to take pediatric cancer. So what happens is children haven't gotten environmental cancers yet, right? They haven't been exposed to 3 Mile Island and things of that sort. They aren't smoking. So what happens is any cancer a child has, is because of something in their genome. So what I did is we took basically the pediatric cancer database from St. Jude's Hospital where they treat children. And we looked at that and says, okay, let's classify and see what it is in the genome that's unique to these different things. So if you've got leukemia, we notice that there's an allele or a change in the genome. And we say, okay, well, this one seems to be identified with pediatric cancer. And then this, with leukemia. And this one's identified with bone cancer. And this one's with skin cancer. And this one's with whatever. And so what was great there, we used that data set. So now we had things that not only work with kids, but when we went and looked into, when we're doing things, we could address that on adults and say, if we check your genome and you're worried about, I might have breast cancer or something like that, we'd be able to go back and say, well, this is the allele, this is the change, the difference in the genome that identifies with that. So it's kind of cool the way it goes. And so I'm not going to get too deep into the rest of that, but two ways that we've been approaching things. In the past, it was like with machine learning, we would go and say, I want to identify a person based on the separation of the eyes, the height of the eyebrows, the symmetry of the face, and all those types of things we'd be looking at. And so what I'd be able to do is use some of these math classifiers, right? And I'd say, oh, based on that, this person is Arjan. Okay, so I know it's Arjan, and there we go, based on those shapes and stuff. Well, with deep learning and neural networks, you basically say, here's my picture, and on that photo, I've got pixels. So I just dropping in the pixels. The pixels become the data, and it's not about his shape or size or anything like this. And I can go and based on, this pixel placement, even if his face was flipped the other way, he may or may not be smiling. If I get enough pictures of Arjan in there, I use that as my data set. And then what happens is it goes through these neural networks and comes out the other side and says, Arjan, okay? So this is just a lot of matrix multiplication going on in here. Each dot coming in, this input layer, might be a different pixel. And then inside here, it's saying, what is the relationship between that and some other part of it, and comes out. Now, I'll give you a better example in a second, but looking at it, think of this as components of a model, and these are just a variety of different models. But if I look at it, I always have the input models, I have the input nodes, output modes, and all these middle nodes, right? The internal nodes. What happens is you'll see that there's a relationship between these, and the node is a property, and the property may be color of something, weight of something, whatever. Like if this was weather, it might be wind speed, direction, humidity, temperature, other things like that. You take all these weather pieces that might go in there. If these were pictures, it would literally say pixel 1, 1, pixel 1, 2, pixel 1, 3, pixel, then it would be 2, 1, 2, 2, 2, 3. And literally, they would have, each pixel would have an input there. But what you do is the nodes are the importance of the property, right? And then you're going to find the connection between them is really the strength of the relationship between those things. How important in weather, I'll go back to weather, is the relationship between the temperature the dry bulb temperature and the wet bulb temperature, or the wet bulb temperature and humidity, and those types of things, wind speed, direction, etc. And so those would be the type of things that you would have between there. So the dendrites, and the are really those interconnects, strength of that relationship. Now, I hope you didn't study that, but I'm going to give you a better example here. If you sort of watch, this is an example of an untrained model, right? And so you have your inputs here. I'm going up down in this case. These are the middle ones, and then you have your output where it does a prediction. Okay, so if I go through this thing, and I'm going to now train this, and in the training process, you're going to see that the nodes are going to expand in size, and the interconnects are going to expand and contract in size too as it starts training it. So I put in one piece of data, it sort of looks this way. I put in a second piece of data, it doesn't quite average between them, but it sort of sees, okay, what mattered again to get that prediction. So if I also get a data set like this data set where it's kittens and dogs, right? I got cats and dogs. I'm going to put this in, and my goal is to predict, is it a cat or a dog if I give it an image? So I've got all these images of labeled data, right? This one is labeled as a cat, and it's a cat. And this one's labeled as a dog, and it's a dog. And so what you do is there's might be hundreds of thousands of pieces of data. In some cases, we do up to millions of pieces of data, but we store that on a disk someplace. We now going to run this through the model. So if we look at it run through the model, we got a system that might have 8 GPUs on it, right? So now what I'm going to do is going to load that up from the 8 GPUs, calculate this. And if you start looking, you can see the size of everything changing a little bit on that model. And you can see them all, they're changing. Okay, now it's finished. And you notice what was on the left, right? They're all the same size. Now you can see this and this are more important than this one. This connection or relationship is more important than some of the other ones. And so that sort of says, now this is my train model. I take that train model, right? And now what I'm going to do is I'm going to take that and say, I'm going to infer or predict. So you talk about training on the left. I'm inferring now that I have a trained model, what this is. Inference is nothing more than prediction. For some reason, data scientists chose to use an interesting word. I wish they had just called it, prediction. But here you go. I took that model. It's over there. Now I'm going to pull that, and I'm going to run that on a smaller computer. I don't need to run it on as big a computer, right? I don't need this big, crazy supercomputer and everything to run this on. I can run it on something smaller, like an edge line. This could be something that's, about the size of a tissue box, right? And so now, and the reason why people don't always say, well, it took so much calculation. Well, if you think about it, during the training, I'm running this on lots of GPUs and sometimes lots of servers, because I'm going to run 1 million pieces of data through here. If I want to infer something, I'm only running one piece of data through here. So where this, if it took me 10 seconds for each one, it would take forever to take 1 million times 10 seconds, right? So 10 million seconds to actually train this model. Whereas if I'm running it through once on this train model, if it took me 10 seconds to figure out if this is a cat or a dog, it doesn't matter. So I could maybe even run this on my cell phone. Now, I got this new data, just took a picture with my cell phone. I popped it in there. I don't know what that is. Well, it comes out that it says it's a cat. Well, what if instead of a cat, right, I want to do something useful? What if I'm the IRS and I say, I want to catch identity theft? And so what I've done is I've got all the 1040s from all the people who were cheating and saying, oh, I'm Joe Smith. Give me Joe Smith's return. And believe it or not, this happens tens of thousands of times each year when all the taxes are being submitted. So what happens is they go and they file with your social security number, and then they get the refund to them. They put in fake data, so they process a refund, and then it goes to them. Well, they rush in there February 1st when they can first start up, right, and say, well before you and I are going to be filing. And then when you file April 15th, it says, oh, sorry, you've already filed. And that's how they find these are identity theft. Well, if I know which ones were identity theft, okay, the 1040s that were filed, the 1040s that are filed good, that's my new data set. They're labeled data. I run that through my model. Yes, it's good, or no, this is okay, and this is not okay. I can start identifying identity theft based on the past. Now I run these through, and again, my next 1040 I run through says okay. So you can see the practical nature of this. Here's a couple examples where the difference, the old traditional, where I say, oh, a car is 4 tires and has a grill and a couple other things. Motorcycle usually is very vertical with a person on the top. That's what I'm trying to identify using instead of I was just saying it was it's feature extraction. So I'm talking about the features of that item. Well, it's tough to tell. Some of these things don't quite fit well into that. Well, now with computer vision, I could train it up, and having seen enough tractors, seen enough trucks in all sorts of positions, front, back, whatever, I can also see those, which is great. And if you look at the old hand-coded computer vision where I did that feature extraction, it could only get to about 75% on the top end, is where it sort of petered out at in terms of accuracy. Well, what we were able to do is now we're getting there so that the accuracy of the computer vision, of the deep learning models, are actually better than humans. Humans are generally about 93% accurate in this, and they're above that now when you sort of look at that. In fact, the same thing with x-rays. If you look at x-rays, we're now on average more accurate than a radiologist. But what we do is we say, use this as a tool. So this way, the radiologist, we go in there and we say, we predict that this is cancer, or we, and then there's a case where you say, this is 100% cancer, this is 100% not. And then what happens, you get that sliding scale where you say, I don't know with this image. It could be either way. And then this way, instead of having the radiologist look at the positively not and positively is, they can spend their time on the ones that they don't know. And so it just speeds up their day. It doesn't eliminate them. It makes them do more valuable work. The other thing that happens is you look at some of the things, like here's a case on the lower right-hand side where there's certain rules out there in an airport. And you can't back up more than 5 miles an hour. You have to have 2 wing walkers out there when you're going on. And this way, using computer vision, they don't get tired. They don't all of a sudden say, oh, yeah, I think that's what happened out there, and not be sure. Well, what happens is computer vision and artificial intelligence, what it ends up doing is says, I can mark all that. In fact, I can tell what 5 miles an hour is, even though I'm looking at a different angle. As a human, I'm saying, yeah, it didn't seem too fast, right, if I was looking. But you've got all those types of capabilities. And it can also coordinate between multiple cameras very easily and be able to use that. So you can see where it makes sense. Now, healthcare is amazing. What's going on there and what we're able to do. I mean, everything from the deep sciences like molecular biology with electron microscopes and cryo-EM. What we're doing is you basically take a sample, you freeze it, and then you hit it with electron beams. And you say, wow, that's really cool. Where's the computer come in? Well, because if you look at it, if you took, remember you were talking about those examples where weather, oh, if I take a square mile or a square kilometer or a square meter, each time it takes more and more compute. When I'm talking about something that I can't see with the human eye, and I'm bombarding it with electrons that are so small, what happens is this actually lights that up, gives us the ability to have high resolution. So within this tip of a needle, you're able to now have something that would be millions of pixels. And so with that, and they're looking for stuff that's larger than that. So basically, they need a supercomputer to be able to perform that. And then they use artificial intelligence to do the analytics on it. Genomics, it's very exciting because it's also very data intensive. And you saw that example that I was involved in with the pediatric cancer and what you can do to be able to do that. And what we're going to do is eventually all of us are going to be probably taking part in personalized medicine, where what is it about my genome that makes me susceptible to these things and yours susceptible to something different, and what we could be also, what means of making us healthy would be most important for us. So what medicine should I take? Because we're finding out like all cancers are not created equal. And drug discovery. What's going on with COVID right now is exciting, because with all that COVID and everything that's going on with drug discovery, they've been able to compress what normally takes 10 years of drug discovery, development, testing, and compress this by using supercomputers. HPE and what we've been doing for the national labs, for National Institute of Health and CDC and others, we've been able to provide a list. And what we did was we took all the compendium, all drugs that were out there, and we sort of said, we're going to match that against COVID and the SARS-CoV-2, which is the technical name for it. And we looked at that and said, okay, what do we think could work on this? So we went from what was, hundreds of thousands of possible drugs and things and compounds, and said, okay, how can we get this down to 5? Maybe 4, maybe 3. And so by using the supercomputers, we were able to say, these are the treatments that are out there. We also looked at all the drugs that existed and said the same thing. Well, now that we know these are the 3 or 4 compounds, let's look at all the drugs that exist today that have those compounds. And maybe there's something already that we can transpose over there. Like that's why you heard of some of the drugs that were there. Some didn't work, right? And some did. And I'm not going to get into politics of which ones did and didn't, but we were able to go and use supercomputers so it was fact-based. Fever detection right now, for coming back to work and to school, a lot of this is about how am I able to go back to work? Well, we're finding fever detection is not as important as all that, but contact tracing is, and other things we do is surveillance to sort of say, how is, where are people in proximity to each other? Are they social distancing? Do they have masks on? Things of that sort that we've been able to use. I talked about cancer research, identification of these things, pandemic tracking, a project that I was involved in had to deal with tracking Zika. And one of the things we found using AI and graph analytics was we could track Zika from where it was in Africa. When it went to the east in Tanzania, there was no encephalitis. Okay, so you didn't have any of the ill effects of encephalitis, but when it crossed the Atlantic, we were able to see and track using a combination of things to see when it mutated and became encephalitis was as part of the disease. And that's why in South and Central America, there were so many issues, and we were able to identify that and try and see what we could do to change it. And then image analysis and patient diagnostics. Just going through these, the patient care, data-driven medicine, medical imaging, improving healthcare communications, and COVID testing, treatment, etc. So a big deal with all that. And so I talked a little bit about medical imaging, but what's key is there's so many different types of images that are out there, and being able to present and use AI for the analysis and identification. An interesting example that MIT did was if you think about it with breast cancer, women get mammograms, and they get mammograms on a regular basis. So first you take a sample of, say there's millions of women got mammograms. So you got a million data set, right? And you take that million data set, well, that's really cool. And you can say these were good, these ones identified breast cancer, these ones didn't. When you say, well, that's good, that's nice, but what's even cooler is the data set says, I took a mammogram 3 years ago, 5 years ago, 7 years ago, 10 years back. Well, MIT got a hold of all of these going backwards in time and said, you know what? I know that in whatever the current time, say 2020, this woman had was diagnosed with breast cancer. What happens if I look back to 2010? And what they were able to do is to say, well, there's nothing indicated on those mammograms, but what do we know about their 10 years ago versus the women who don't have cancer 10 years ago? And they're able to come up with a way to predict 10 years earlier whether or not that woman was going to get breast cancer. So very interesting on what's able to do. Cybersecurity, I talked a little bit about this, but one of the things that's very state of the art is being able to say, I will take every user or device, user or entity, and it's called user or entity-based analytics. And what it does is says, I'm going to profile that. Well, a printer acts like this, okay? And so if a printer starts FTPing somebody, well, that's not a printer. Printers don't act like that. I bet you that device has either been hacked or someone replaced that printer on that port and plugged something else in. What if I say, okay, all my system admins, they generally start at this time or that time or some different ones. So I've got a profile for all system admins, and then I got a profile of Steve Heibein, who's the system admin. And so I noticed that Steve, he shifts his work a little bit. So Steve's the afternoon shift. He's not doing the morning shift or the daytime shift. So that's okay. That's part of what's different about him. But what I could do is say, okay, his Mondays are sort of like this. His Tuesdays are different. His Wednesdays are different. So now I got a profile for the 7 days of a week, over time and how he's done. And sure, it shifts and I make changes to it. AI changes that. So what happens is also when I start looking a lot different than a standard system admin, or I start looking a lot different than myself, maybe something's happening. And so what they can do is say, well, that's a little bit odd for him, but let's see if anything else happens. And the AI keeps monitoring, and the AI says, well, that's really odd for him. And then finally it says, now I'm going to alert the NOC. So I'll let the Network Operations Center know something's changed. So what we're doing is we're using AI to do that. And we can identify, again, there's no reason why the VP of Finance is in the engineering database. Makes no sense, right? So some of these things seem obvious, but something's subtle. I have root permission. I'm a system admin. I could roam any place. I'm allowed to, but do I normally? And so that's what's cool about this. You can find things that are more use patterns. The applications in a place where it's at, like quality control and prescriptive maintenance and such, HPE actually does this today, and we've been doing it since 2010. Every one of our servers and every one of our storage devices has the ability to basically say, phone home. What we do is we have predictive maintenance say, we know what's going on. You're telling me some telemetry information, what's the heat of the storage device, what's the operation time of each one of those spinning disk or SSDs, how much is its use cycle, how's that compared to other spinning disks or SSDs, what has been, when was the last time it was replaced? And then it says, I've got this database of all these servers and storage around the world that are HPE. And then we say, well, based on that, whenever somebody's had that many use cycles and that much temperature over that length of time, they're gonna fail within the next 30 days, we predict. So what we do is we use that prediction to say, let me go and send somebody out on site and so the AI actually schedules the service person. It actually alerts the customer and also FedExes out whatever they're going to be replacing. And so that's with predictive maintenance. We're doing that now with aircraft and with other things to be able to say, I know what you need to replace. I can predict that. And so instead of sitting there and going, a good example is windmills, right? You've got all these wind generators. they're not easy to maintain, right? They're big, they're burly, they're everything you're bringing up there, you got to stop them, you got to bring a crane to get everything. So what you want to do is you want to say, if I can, instead of saying every 3 years I got to replace all these parts, wouldn't it be better to say, I'm going to replace a part when it before it fails, because if it does fail, it's catastrophic, because these things could fall and fly off and do whatever. So you can imagine if a blade fell off or something happened in terms of the inside gears. So you want to catch it beforehand. And so what it does is it says, I predict this. So whether instead of going out every 3 years, no matter what, and paying for all those parts, wouldn't it be great for the ones that are going to fail early, fix them, but the ones that are going to run for 6, 7, 8 years, wait, And so this way you've got a way to actually save money, and it pays for itself. Surveillance, we got all sorts of ways to do things now that we can identify when someone leaves an item behind. If they exchange items, we can follow that. Obviously, facial recognition, monitor how people are in queues. We're doing a lot of this in stores. In stores, they can say, show me a heat map of where people walk. So what I can do is I can say, well, if in a grocery store, they actually charge for placement. So if Kellogg's wants to be in a best place possible, what they can do is show the heat map and say, there's where people walk most often. Here's where they are. This is when the ones who pick up, cereal, breakfast cereal, this is where you want to be. Well, that's more expensive. And then you might have somebody who says, well, I need to get in and I don't care. I'll take the corner one in the dark because I need the cheapest place because I can't afford what Kellogg's can afford. You got different ways to charge for different spots on your floor shelf, your floor space there. Text to speech, we're getting better and better. We're only talking to, I don't even want to say the names of the devices in our house because mine will start talking back to me. But, with what we're able to do now is pretty incredible. And the autonomous driving cars, I mean, really, if you think about it, level 5, fully autonomous, I think that's still a ways off. But when you look at what we can do, level 3 and level 4 are being achieved right now in terms of what they can do in terms of driver assistance. A lot of other areas, vision, you can see speech, text. People don't realize there's a lot more to text. You say text is easy, right? I can search text. Well, a lot of times what you want to do is you want to do this thing called sentiment analysis. I want to understand the sentiment of what was written. Are they, like if I'm looking at tweets and stuff, I might want to know if they're talking about my brand. Are they happy about my brand? Are they sad about my brand? Oh, I can have a person do all that. That would be the world's most boring job. And it might be accurate or inaccurate, but the one thing is when the computers do it, they're actually pretty darn accurate, and what they do is they can do this relentlessly, right? They don't get tired, they don't fall asleep, they don't worry about any of this stuff, they don't take coffee breaks. So you basically have them, and then you say, ooh, over time, I can see that I'm getting 60% of the people are happy, but there's still this 10% that are really angry, that type of thing. And other things I mentioned, drug discovery, advertising, fraud detection. Some of the things with video analysis, here's what I was talking about, what a heat map looks like. See this in a space, and you can sort of say, okay, this looking at, where these are, this would be like where they play poker, video poker and things of that sort. So I could say, okay, which games are they most interested in? Okay, I see they use this one, they ignore that one, and so on and so forth. And so you can sort of just visually see and get a better idea for that. With face recognition, we're so good now, we can actually recognize faces with a mask on. So if you've got a COVID mask, we can identify that with a limited set. Okay, if you already know these are all the people who work for your company and they're coming in with a mask, we can identify those as they're walking by. They don't even have to look into the camera. And so with crowd counting and a variety of other things that are out there. One of the things that's really weird or funny or however you want to look at it is these are all faces of people that do not exist. Okay, these were computer generated. So these were not somebody else's pictures. Everyone was computer generated, the background, the everything, the look. What they did is there's actually a website says thispersondoesnotexist.com. And so what's cool about this thing, thispersondoesnotexist.com, is they show you how you can generate new pictures. And what they do is on the left, I've got real data picture of people. Then I've got this synthetic generator stuff. So what I can do is I can put in noise and say this amount of noise into the picture. So what happens is I can generate, like I said, a variety of people. I could even generate a family if that's what I wanted, or a variation. I could say, okay, I want this person, but I want a young version of them. You get the idea. And a lot of what's going on with movies are synthetically generated content. Sometimes you'll see a crowd scene, and those will all be synthetically generated crowds. Other things, satellite imagery and what they're able to do there. A lot of what they're doing now is with surveys. Governments use these things to be able to identify surveys and for doing tax rolls and understanding, the housing things that are out there. But just industry in general, looking at these things, oil and gas is very big in this for trying to do discovery of fuel. And so what they'll do is they'll actually vibrate the ground, and they'll try to, from that vibration, be able to identify what is liquid oil in the ground, what is solid rock, what is the type of rock, and so on and so forth. Mind you, their vibration is all these big sonic things that you may or may not even feel, but they're at a frequency level that gives them enough information back that they can identify what is underground. I talked about, facial recognition, telcos use this for data, for customer acquisition, et cetera, in the national labs. Here's this, I'm going to skip this for time. A couple things. This is part of like that clustering that we did with to identify different cancers. But what graph analytics does is say, I can cluster and see what is different or unique about different things and be able to identify that. And a lot of times you'll have these relationships of billions of edges. And then what happens for those of you that aren't data scientists, right? I don't know this higher level math. Is AI out of the question for me? Well, there's some real cool things called, in this case, H2O's product called driverless AI. Think of it as it's auto ML, so autonomous ML. So it uses machine learning to create machine learning. And so what's cool about that is it'll help data scientists and stuff too, but what it really helps is what I call a citizen data scientist. I know my data, but I don't know data science. Example of that is I'm at the National Bureau of Standards, or I'm at the Census Bureau. That's a better example. I'm at the Census Bureau. I understand census data. Well, what happens if I want to do analysis on it and see how the trends are? How have people trended older over time? How have affluence trends changed over time? Is there migration to the city, out of the city? Is there difference on the East Coast versus the West Coast? I know that stuff, but let me use AI to do it. Well, that's what something like H2O AI does. Basically, you say, okay, give me your data source. And then what I'm going to do is take that data source. I'm going to split, that one went all the way through. But basically, I split that data source. I hope I can get it up there. Yeah, please don't go forward on me. So what happens is, forgive me for that. But basically, I'm going to do this a couple times. So the modeling, you see it here. We split it in half. And then what we do is the first part, the X part, is for the training. The Y part is for the testing. We run it through, and at the end, it actually gives us a prediction for us. So it's pretty interesting software to be able to help those who know their data but don't know data science to do machine learning. I hope that helps. This was a lot of information in a very short period of time, and I know overstayed my welcome here.
Hey, Steve, thanks so much. So Steve and Bryan, you can try to activate your cameras And so for the Q&A session, we do have a couple of questions. And for today, our industry moderator and co-host is Bryan Bemley. And Bryan is an IT security specialist with Accenture Federal Services, and he's also the CIO for Joint Education Facilities, which is also, we know affectionately as JEF. And since the age of 4, Bryan has always been fascinated with technology. That was his leap into back in the day when he was 4 years old. We had DOS, just the disk operating system. And since then, he has immersed himself in many different areas of computer science, information technology, artificial life, high performance computing, web and graphic design, cloud computing, and cybersecurity. And as many of you know, both HPE and JEF have been national BDPA mission partners, since the mid 1980s. And today we connected a few dots for you. And so right now we're going to get underway with the Q&A session. And one of the first questions we had in our Q&A section was about level 5. We have a question that wanted to know what is prohibiting industry from reaching level 5 for autonomous cars.
Well, the biggest challenge is that we haven't got enough use cases. If you think about it, it's the corner cases that happen. It's the people walking out on the curb. People don't act rational necessarily. They're watching their cell phones. So it's those types of corner cases. So we're trying to develop more and more data. They're collecting data like crazy. If you look at an autonomous car when it goes out for training, what they're doing is it's going to be terabytes of data that they're going to bring back for every 8-hour session. Some people say it's between 1 and 4 terabytes. And you think about it, you know what a disk size is. Now imagine that you got to process that and you got to collect that. You're really looking for petabytes and petabytes of data. You need probably, it could be as much as an exabyte of data to be able to get enough training for enough different situations. Fog is still a problem. Nighttime is still a problem. Those are real things that are probably the biggest difference. So once they get enough ability to do that, and I think that's going to help out.
Thanks so much, Steve. That was a good
yes,
question.
I'd like to.
Go ahead, Bryan.
Oh, let me piggyback on that, Perry. So I also want to take into account that when you're using these different algorithms, it's easier to create a prediction with information you already know. And since human nature in itself isn't predictable, that also ties into account how these simulations and algorithms can predict what's going to happen on the road, for example. So if there was a road of all autonomous vehicles, they can share that information and make predictions easier. But because of the unpredictability of human nature, that also makes it difficult.
Yeah.
Yes, sir. And that question came from one of our IT Showcase high school students. Ms. Gordon, thank you so much for your input. Another question we received from Mr. Nixon. Wanted to know about how may we receive our recording later in the session. We will make that available through all of our channels as we normally do. And Mr. Nixon is also in our Northern Virginia area, and we're actually standing up Northern Virginia. I have a couple more questions earlier, briefly about smart cities. And Steve, you alluded to a lot of that earlier. I think it was outstanding presentation. So basically, we hear the term infrastructure, we hear the term smart cities. So Steve and Bryan, if you can, just share just a few inputs as to, if I'm a high school student right now, what type of courses do I need to take, or what type of internships should I look forward to as I move into industry?
Right.
All right, I'll start. Since I work for Accenture Federal Services, which is a subsidiary of Accenture Inc. And one of the things I would recommend for high school students and or college students is to start beefing up on your math skills, because a lot of the information that the algorithms use are math-based, because a lot of the data can only be modeled in a mathematical way. So I would also look at the different social sciences and try and tie in your likes and the subjects that you're most interested in into the field, because that way you can create a different what's the word I'm looking for? You can create a different perspective on how these algorithms work versus what's already been tried, and that helps train the algorithms to get better predictions.
I would say just across the HPC industry writ large, the HPC community, if you can describe maybe what an entry level position or role would look like. And then again, if I'm a college student or if I'm actually upskilling my career from one career to another area, what would that look like with respect, as you see in the future for AI?
I think what I've been seeing with AI and HPC, it's almost been two different ways. Those coming into AI are generally younger, and those that are in HPC are generally older. And so what's happened because of that is right now there's a skills gap and an employment gap in HPC where they're saying we don't have the replacement engineers. Most of those that have been doing HPC are like me. I'm about 180 years old and well preserved. But so what's happened is they're pushing. So places like NASA, the U.S. Department of Energy, Department of Defense, they're all pushing to get more and more young people into it. And so if you look at a place like the National Security Agency, for those of you that are in the Washington, D.C. area, Virginia, Maryland side, they're hiring like crazy. They love high school interns. And so what you'll find is with their program, they'll be hiring, dozens to hundreds of high school interns. And their whole goal is to help teach them. They bring them in on interesting things, and as their skills grow, they give them more and more to do. And so you'll see they'll get more computer skills, more math skills, more technical skills on the different areas. And I think I like that. NASA, same thing. NASA has multiple supercomputers. And whether you're on the East Coast, West Coast, or any of the other labs, there's ones in Huntsville, Alabama. There's ones in Stennis, Mississippi. So it's not just when people say, "Oh yeah, that's here and there." No. There's a big center in Ohio. So look around at those. Those are great places to get skilled up.
Yes, sir. And Steve, the good news is, as we touched on earlier in some of our conversations, the intelligence community has been a very strong mission partner to BDPA. In fact, when you mentioned the agency here in Maryland, they have attended several of our conferences in the past. I know several students have actually participated in some of their info sessions. So very, very good opportunities there. So Bryan, if you don't mind, we're going to close up. Give us a few pointers as to your experiences as an intern. I know you were an intern in the DoD side of the house. And also, real quick, give us an update on BDPA and JEF and what you see down the road.
Okay, so my experience as a DoD intern, I've been exposed to a whole lot of different technologies, the access grid and grid computing, high performance computing. We also used to go to the supercomputing center every year, and Jeff was actually gifted a 6-node mini cluster called Little Fee, and was run on a Debian-based operating system called BCCD that we can teach our students parallel programming with MPI and OpenMP. And it also has NVIDIA GPU, so we can teach CUDA programming as well. So what I see down the road for BDPA and JEF, currently JEF is trying to revamp the curriculum so that we can focus more on high performance computing, cybersecurity, and data science with different initiatives. Like one initiative is creating a SOC for JEF students to learn the actual full cybersecurity cycle. Another initiative we're trying to do is we're currently trying to upgrade our rack of servers so that we can create our own private cloud, and also to do some HPC work. Like we have some Gen 2 and Gen 3 ProLiants, so we really need to get some new hardware refreshing to allow students to be exposed to this technology. And with that exposure, it'll allow our students to do more research projects in order to bring it to the BDPA community, and it'll allow us to further enhance our exposure and our presence in the HPC community and cybersecurity.
Thanks, Brian. Appreciate it. So, Steve and Brian, thank you so much for participating in today's info session. This is outstanding. Again, we will put this into a full-blown presentation. It will be airing on our Popular Technology TV network, as well as all of our social media channels and our YouTube channel. And as a reminder to our audience, up next in November 7th and 14th, HPE will be joining us again. The topics will include autonomous operations, AI and compute at the edge. And then finally, we'll have edge to core analytics. So stay tuned for that. And again, follow us on bdpatoday.com or Popular Technology TV. And if you haven't done so already, please update your memberships at bdpa.org. Thank you very much. I am your host, Perry Carter, and have a great weekend.
Thanks, Perry.
Yes, sir. Thank you guys too.